I have cut the previous video quite short, but I wanted to show you guys this. This is a piece of obsidian which my previous student from art science sold me. Yes, this is obsidian, and it's the one here in this picture here. It's not considered as a mineral but as a mineraloid because it's glass instead of having a crystalline structure. If you hold it, it's quite cold, and like it's like holding a chunk of glass. Like some of its edges are even sharp, so it's really just like glass. So not crystalline structure but a mineraloid. This is just one of my mineral collections. Some of my mineral collections are in school. So yeah, this is what we have left of our mineraloids. Okay. So you can classify chemicals in different ways, and one of which is through the composition or chemical composition. So there are minerals which is first made up of native elements. When we say native elements, they are undiluted, pure, or uncombined minerals. So for example, iron. So it's just a chunk of iron, and that's an example of one native element mineral in metallic form. We also have sulfides, so sulfur containing groups. So usually sulfur, they're very brittle and yellow. Oxides, so mostly oxygen containing groups. Halides or halides, which contains your halogen ions. Your carbonates, so usually white information carbonate group. Sulfates, there sulfate groups. Phosphate groups, your silicates, which are very common because as you can remember from our graph, silicates and oxygen are the most dominant or the most common minerals. That's why quartz, which is a silicate mineral, is very common. Okay, and other organic minerals. So for example, they contain organic carbon. So that type of carbon came from organic minerals or organisms, but it has already been decomposed, and it was not made by organic processes but normal geologic processes. Okay, so those are the 9 types of minerals based on chemical classification. But in terms of the number of minerals we have on Earth, we have around 4,000, I think, yeah, including the synthetic ones. So 4,000 minerals. So how are we going to classify them? So before, when we started the earth science, studying earth science, we weren't able to identify them based on chemical classification, but based on their physical properties. That's why even if you don't have like an analysis of their chemical composition, you can already differentiate the minerals we have today. So we will be discussing how to identify minerals using their physical properties. First, you have your color. So of course, color may be one of the things that you can use as a basis. So as you know, color is a visual measure based on the wavelength that you perceive in your eye. But using color in minerals is not reliable because there are several minerals which comes in different colors. For another example is quartz. So quartz is quite common and they come in different colors. So there's pink, there's blue, there's green, but again, there's still quartz. So there are also minerals that looks the same but is actually quite different. So color may be like your first like pseudo basis, but it's not, shouldn't be your final characteristic when using it for identification. Okay, instead we use something called a streak, and for this you need a streak plate. Usually they use like a black one rather and a white one. So a streak is the mineral when what the mineral leaves behind on the streak plate if you like rub it against its surface. So for example, like if I take this mineral here and then I rub it against the plate, what will be the color that will be left? So for example, Let's get my laser pointer. In this picture, you have a hematite featured. So it's color black, but if you look at the material that it left on the streak plate, it's actually red because hematite is full of iron. Thus, hema, because it means iron. Next, we have also, I think this is pyrite here. So pyrite looks golden, so it's like fool's gold, but if you rub it against a streak plate, it's color gray, so it's not real gold. Okay, so this is like a short video, I think. There we go. So showing you how to identify minerals using a streak plate. So let's just wait for that to load. Alright. See, I think what he's holding is pyrite. So it looks gold as you can see, but if you rub it against a streak plate, it leaves like a greenish gray streak. That's something you could do. Like if you're buying sketchy gold, you could try. The normal gold doesn't leave a streak. So if you like test it using a streak plate, it shouldn't leave any color behind. Okay, so that's just the example we have. Okay, so that's the streak plate. Next, luster. So luster refers to how the mineral reflects light, and we usually refer to it as either metallic or non-metallic. So for example, here in this image, it's obviously metallic in nature. So gold, silver, copper usually have this sheen type of shine to them, versus the one that's like this, you can immediately say that it doesn't shine like copper, or like glass. It more like shines like glass, so those are different. So sometimes it's more of a pearly nature instead of having a metallic luster. So just though for simplification, we will just refer to this as luster, being metallic or non-metallic. Next, hardness. So we can measure the hardness of different materials based on its ability to scratch other materials. For this, we use something called a Mohs hardness scale. And there it is a scale reference from 1 to 10. And this is what it looks like. So talc is a very soft material that I think you are very familiar with. This is something you use for powder, like face powder. So as you can feel, it's very soft, and that's number 1 on the Mohs hardness scale. So the powderized form of talc here is, that's what we use for face powder. So in the Mohs hardness scale, that's 1. Then that goes up to the diamond, which is 10 in the Mohs hardness scale. So there are actually other minerals that is above 10, harder than diamond, but for simplicity's sake, we will just focus on the 1 to 10. Okay, so again, the ability of the Mohs hardness scale, or the way we measure it, is its ability to scratch other minerals. So for example, if I take apatite here, apatite number 5, I am sure that it will scratch any of these objects because apatite is harder than fluorite, calcite, gypsum, and so forth. So that's how to measure. We usually use glass, which has an average of like 6. So for example, if the object of your mineral can scratch the surface of a glass, we can say that the Mohs hardness of that mineral is above 6. If it cannot, then it's lower than 6. Okay, so some representative minerals which will allow you to further understand the Mohs hardness scale. So for fingernails, that's only 2.5. The copper coin is 3.5. A steel knife is 5.5, and then a stick plate is 6.5. Okay, so just to test if you really understand how the Mohs hardness scale works. Okay, can topaz scratch quartz? So topaz sits 8 in the Mohs hardness scale. Can it be used to scratch quartz? So yes, because topaz is harder than quartz, so we can surmise that it can scratch quartz. How about using apatite, which is number 5, to scratch corundum, which is number 9? Will it work? Okay, so of course not. So apatite is only number 5 and the Mohs hardness scale, so we cannot use that to scratch corundum there. So that's how the Mohs hardness scale works. Okay, so just another visual representation of our Mohs hardness scale. This is, by the way, named after Friedrich Mohs, which is a German mineralogist. Okay, so crystal form, number 5. Another way to identify minerals is to look at their natural formation. So if you were like walking in the environment and you find this mineral, what does it look like? So there are different ways on how they could form based on their chemical structure. So the chemical structure will definitely influence how they are formed. So the crystal form, or some books may refer it as a habit. So some may be cubic in nature, some are prismatic, which looks very mysterious. That's why maybe they sell it for like mystical healing stones, but that's just the normal form of the mineral. And then we have your amorphous ones, which doesn't have a definite shape. Okay, so we can also identify minerals based on how they break, and how they break also relies on their chemical composition. So first other interesting characteristic about minerals is cleavage. So the tendency of a mineral to break along smooth planes, because based on their crystal structure, they have zones of weakness. They create like these areas in the internal structure wherein when force is placed on the mineral, there is a straight weak line along its crystalline structure. That's why if you break them, it's just straight. Okay, so for example here, these are already cracks, but they're like perfectly straight cracks just because of their crystalline structure. So when they break, it's flat. So just remember, it's the opposite in terms of your usual jokes. If there's a cleavage, it breaks flat. Okay, so one video example. So this is calcite, which is very fun. It's a video of calcite breaking, and you can see it's still straight. Even the small shards that it left behind, it's still straight. So again, straight, that's a cleavage type of breakage. There, okay. Let's just shift that to next, which doesn't allow me to. Hold on, guys. Okay, next, fracture. So the fracture is the more common one. So it's like the non-straight. So fracture is the normal broken surface. So like this, the fractured one. So it doesn't have like a straight edges or perfectly cleavage planes. Instead, it doesn't have a pattern to it when it breaks. Of course, like in the internal structure, if you look closely, there is a pattern because it will still break based on in its chemical composition. But it's not like the cleavage with straight cuts when they break. So if it's unbroken, if it's in a broken shape that doesn't follow like a visible pattern, that's called fracture. So it's either cleavage or fracture. And then physical property number 8 that we could refer to is the density of the given mineral. You may know the story of, I think, Eureka. So there was one philosopher who wanted to know if it's real gold or not. So he used the specific gravity, the concept of specific gravity, in order to figure out if it is real gold or not. So the amount of water displaced by a mineral sample is considered as its specific gravity. It's more of a ratio. It's ratio to the amount of water it's displaced to its normal weight. That's the specific gravity. Okay, so let's talk more about how the crystal structure can dictate its physical formation. So both diamond and graphite are made up of carbon, but their framework or their internal structure is different. So as you can see, for diamond, it has strong covalent bonds among its carbon, but unlike graphite, which is more brittle, it forms these sheets. That's why if you break carbon, if you break graphite, it follows a cleavage because it can break into these straight planes, unlike diamond, which has like a strong covalent bonds within. Okay, more examples why certain objects, certain minerals have specific shapes. So table salt looks like little cubes or little squares because of their internal structure like this. Okay, then gold is very useful because you could shape it into different ways. It's very malleable. So that's the term. It's very malleable because the atoms of gold are densely packed, and you could, since they are densely packed, you could easily shape them because it follows the shape of its container because it's densely packed. There. Okay, so just more examples. So the crystal form or the habit, and it's showing here like a prismatic habit of a crystal or a mineral. So again, cleavage is creating this flat sheets. I think this is mica. Mica bricks in sheet formation. So that's a cleavage. Then fracture, it doesn't have a visible structure in its breakage. So color is one physical property but not a reliable property when identifying minerals. And then the luster, or how they shine, metallic or non-metallic. You can measure hardness using the Mohs hardness scale, and you could also test certain minerals based on their effervescence or how they will react if you expose them to acids. So for example, if I drop sulfuric acid in a mineral, would they fizz up, like produce bubbles because the gaseous elements have been released, or there's no reaction? Okay, so that's effervescence. The streak or the color that it leaves behind on a streak plate, if it has magnetic properties, is another characteristic, and also its specific gravity. Okay, so those are all the physical properties of our minerals. If you have any questions about this discussion, you can message me through our Microsoft Teams or through course messages. Now, the next part will be on the processing of mineral ores.